The concept of cosmic inflation is a fascinating and profoundly counterintuitive idea in modern cosmology. It proposes that in the very first, fleeting moments of its existence, our universe underwent a period of astonishing, hyper-accelerated expansion. This is a story that begins not with a slow, gradual unfolding, but with a cataclysmic and almost unimaginable burst of creation. The theory, first introduced in the early 1980s by the physicist Alan Guth, suggests that in a tiny fraction of a second after the Big Bang, a period of time so short it is almost impossible for the human mind to comprehend, the universe expanded at a rate that was vastly faster than the speed of light. This was not a violation of Einstein's theory of relativity, as it was not matter that was moving through space, but space itself that was being stretched, the very fabric of reality being inflated like a cosmic balloon. This brief, but incredibly violent, period of exponential growth is thought to have smoothed out any initial irregularities in the nascent universe, leading to the remarkably uniform and isotropic cosmos that we observe today. The primary evidence for this strange and wonderful idea comes from our detailed studies of the cosmic microwave background, the faint, ancient afterglow of the Big Bang. When we look out at the CMB, we are seeing a baby picture of our universe, a snapshot of the cosmos when it was just 380,000 years old. And what we see is a universe of almost perfect uniformity, a thermal bath with a temperature that is the same in all directions to an accuracy of 1 part in 100,000. But imprinted on this smooth background are tiny, almost imperceptible temperature fluctuations, ripples in the primordial plasma that were the seeds of all future cosmic structure. The statistical properties of these fluctuations, as measured with incredible precision by satellites like the Planck Observatory, are a stunning confirmation of the predictions of the inflationary model. The data reveals a universe that is geometrically flat, a key prediction of inflation, and the specific pattern of the fluctuations provides a direct window into the physics of the universe's first moments, suggesting that the grand macroscopic structure we see today, the vast web of galaxies and clusters, is a fossil, a macroscopic manifestation of the tiny quantum fluctuations that were stretched to astronomical scales during the inflationary epoch. But the theory of inflation does more than just explain the universe we see. It also makes a bold and testable prediction that this period of violent, accelerated expansion should have generated a faint, primordial background of gravitational waves, ripples in the very fabric of space-time. The search for this faint, gravitational whisper from the beginning of time, through experiments like LIGO and future, space-based observatories, is one of the great ongoing quests in modern physics. If detected, it would be a definitive, smoking gun confirmation of inflation and a new and incredibly powerful window onto the birth of our universe. The theory of cosmic inflation, in its most basic form, is a story of a single, dramatic event at the dawn of time. But in its more modern and more speculative developments, it has blossomed into a much grander and far stranger vision of reality, the concept of eternal inflation and the multiverse. This idea, pioneered by physicists like Andre Linde and Paul Steinhardt, suggests that the process of inflation, once it begins, may never truly end. Instead, it becomes a self-reproducing, eternal process, a cosmic fractal that is constantly spawning new bubble universes. In this picture, the end of inflation in our own local region of space was just that, a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate, and constantly and randomly, giving rise to new bubbles, new Big Bangs, new universes. Our entire observable cosmos, with its hundreds of billions of galaxies, is just one tiny, and perhaps insignificant, bubble in an infinite, bubbling foam of other worlds, and these other worlds may not be like our own. The specific way in which the inflationary energy decays in each bubble can lead to different vacuum states, which in turn can result in different fundamental particles, different forces of nature, and different physical laws. There could be universes with more or fewer dimensions of space, universes where gravity is a repulsive force, universes where the chemistry of life is impossible. Most of these universes would be sterile, bizarre, and inhospitable wastelands. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle that requires a special and perhaps supernatural explanation. It becomes a simple and almost mundane selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves living on a planet that is not too close and not too far from its star. It is the only kind of place where beings like us could evolve to ask the question. The multiverse, in this sense, provides a scientific, albeit untestable, framework for the anthropic principle. This is a vision of reality that is almost impossible to fully comprehend. A vision that pushes the boundaries of our imagination and our very definition of what the universe is. It is a vision that is deeply unsettling to some, as it seems to remove any sense of specialness or purpose from our own cosmic home. But it is a vision that is also, for others, a source of profound wonder and liberation. A vision of a cosmos that is infinitely more creative, more diverse, and more magnificent than we ever dared to imagine. The development of the theory of cosmic inflation is a beautiful case study in the process of scientific discovery. It was not a theory that was born in a single eureka moment, but was the result of a long and often difficult process of grappling with the deep conceptual puzzles that the standard Big Bang model had left unanswered. The theory's primary architect, Alan Guth, was not a seasoned cosmologist when he had his breakthrough insight in 1980. He was a young particle physicist who was trying to understand the implications of grand unified theories, the ambitious and as yet unproven theories that attempt to unify the three non-gravitational forces of nature into a single underlying force at very high energies. These theories predicted that the early universe should have gone through a series of phase transitions, similar to the way that water freezes into ice. And they also predicted the existence of a number of exotic and unwanted relics from these transitions, like magnetic monopoles, that should have been produced in vast numbers and that we do not observe today. It was in the process of trying to solve this monopole problem that Guth stumbled upon the idea of inflation. He realized that a brief period of exponential expansion, driven by the energy of a false vacuum state associated with the gut phase transition, could not only solve the monopole problem, but could also, as a kind of wonderful and initially unintended side effect, solve the horizon and flatness problems as well. Guth's initial model, however, had a fatal flaw. It did not have a graceful exit from the inflationary phase. His universe was full of colliding bubbles that would never coalesce into a smooth, homogeneous cosmos like our own. It was other physicists, like Andre Linde and Paul Steinhardt, who, in the years that followed, developed the more sophisticated new inflation and chaotic inflation models, which provided a more plausible and elegant mechanism for ending the inflationary phase and for transitioning into the hot Big Bang. This story is a testament to the fact that scientific progress is often not a linear path, but a messy, collaborative, and iterative process. A process of bold conjecture, of rigorous critique, and of collective, creative problem-solving. It is a story that also highlights the deep and fruitful interplay between different fields of physics. The solution to a deep puzzle in cosmology, the puzzle of the universe's initial conditions, came not from a cosmologist, but from a particle physicist who was working on a seemingly unrelated problem. It is a beautiful example of how the search for a deeper understanding of the very small, the world of quantum fields and fundamental particles, can lead to a revolutionary new understanding of the very large, the world of galaxies and the expanding cosmos. The theory of cosmic inflation is now a cornerstone of modern cosmology, a standard and essential part of our story of the universe. But it is a theory that is still, in many ways, a work in progress. We do not yet know the precise identity of the inflaton field or the exact details of its potential energy landscape, and we are still searching for the smoking gun observational evidence, the primordial gravitational waves that would be a definitive confirmation of the theory. The story of inflation is a story that is still being written, and it is a story that is a beautiful and powerful testament to the restless, creative, and endlessly curious nature of the human mind itself. The theory of cosmic inflation is not just a beautiful and elegant idea, it is a powerful scientific theory that makes a number of specific, testable predictions. And in the 4 decades since it was first proposed, it has passed a remarkable series of observational tests, moving it from the realm of speculative conjecture to its current status as the standard and most well-supported paradigm for the origin of our universe. The most important and most precise of these tests has come from our detailed observations of the cosmic microwave background. The CMB, as we have seen, is a snapshot of the universe when it was just 380,000 years old. And the tiny temperature fluctuations in this ancient light are a direct fossil of the primordial density variations that were seeded by inflation. Inflationary theory makes a number of very specific predictions about the statistical properties of these fluctuations. It predicts that the universe should be geometrically flat, which means that the angular size of the fluctuations on the CMB sky should have a very specific characteristic scale. It predicts that the fluctuations should be Gaussian, meaning they should have a random, bell curve-like distribution. And it predicts that the power spectrum of the fluctuations, a measure of how their amplitude changes with angular scale, should be nearly, but not quite, scale invariant. This means that the fluctuations should have roughly the same strength on all scales, but with a slight red tilt, a slight tendency for the fluctuations to be stronger on larger scales than on smaller ones. The detailed, all-sky maps of the CMB created by the DAUMAP and Planck satellites have tested these predictions with stunning precision. And the results have been a triumphant confirmation of the inflationary paradigm. The universe is observed to be flat to within a fraction of a percent. The fluctuations are observed to be almost perfectly Gaussian, and the power spectrum is observed to be almost perfectly scale invariant, with just the slight red tilt that the simplest models of inflation predict. This is a remarkable achievement. It is a direct observational link between the largest scale structures in our universe and the quantum fluctuations of a hypothetical field in the first fleeting moments of time. But the ultimate and most sought-after confirmation of inflation would be the detection of a specific and unique signature in the polarization of the cosmic microwave background. Polarization is a property of light that describes the orientation of its electromagnetic waves. The CMB is expected to be polarized. And this polarization can be decomposed into 2 different patterns, known as E modes and B modes. The density fluctuations seeded by inflation are expected to produce only E mode polarization. But inflation also predicts the existence of a primordial background of gravitational waves, ripples in the fabric of space-time itself. And these gravitational waves would have left a unique and unmistakable imprint on the CMB, a faint swirling pattern of B-mode polarization. The detection of these primordial B modes is the holy grail of observational cosmology. It would be a direct and unambiguous confirmation of inflation, and it would also provide us with a direct measurement of the energy scale at which inflation occurred, a glimpse into the physics of the universe at energies that are 1,000,000,000,000 times higher than anything we can achieve in our terrestrial particle accelerators. In 2014, the BICEP-2 experiment at the South Pole announced that they had detected just such a signal. The announcement was met with a wave of excitement and fanfare, but it was, unfortunately, a false alarm. It was later shown that the signal they had detected was not from primordial gravitational waves, but was due to the polarized emission from dust within our own Milky Way galaxy. The search for the primordial B modes continues, with a new generation of more sensitive, ground-based and balloon-borne experiments. It is a search that is pushing the very limits of our observational capabilities. A search for a signal that is incredibly faint and is hidden behind a complex and confusing veil of galactic foregrounds. But it is a search that is worth the effort, for in that faint, swirling pattern of ancient, polarized light lies the key to one of the deepest and most profound secrets of the cosmos, the story of our own. Inflationary birth. The theory of cosmic inflation, born from the desire to solve the puzzles of the Big Bang, has, in turn, opened up a new and even deeper set of questions about the ultimate nature of our universe. The simple and most successful models of inflation. The slow-roll models are based on the idea of a single, simple inflaton field that slowly rolls down a smooth, potential energy hill. But there is nothing in our fundamental theories that tells us that this must be the case. The landscape of possible quantum fields and their potential energy surfaces is a vast and largely unexplored territory. This has led to the development of a whole zoo of different inflationary models, each with its own unique set of assumptions and predictions. The chaotic inflation model of Andre Linde, for example, proposes that the initial conditions of the universe were not smooth and ordered, but were, as the name suggests, chaotic. The inflaton field could have had different, random values in different regions of space. In some regions, the field would have been at the bottom of its potential well, and no inflation would have occurred. In other regions, it would have been high up on its potential hill, triggering a period of rapid inflationary expansion. This model leads naturally to the idea of a multiverse, with our own observable universe being just one of a vast number of other causally disconnected regions of space that also underwent inflation. Other models propose a more complex inflationary sector, with multiple interacting inflaton fields. These multi-field or hybrid inflation models can lead to a richer and more complex set of observational predictions. For example, they can produce non-Gaussian fluctuations in the cosmic microwave background, specific, non-random patterns that could be a telltale sign of the interaction between different fields in the early universe. The search for these non-Gaussian signatures is a major goal of the precision cosmology experiments like the Planck satellite. String theory, our most ambitious and mathematically sophisticated attempt at a unified theory of everything, also has its own unique take on inflation. In brain inflation models, the inflationary expansion is driven by the motion of brains, the higher dimensional objects that are a key feature of the theory. Our own three-dimensional universe could be one of these brains, and the period of inflation could correspond to a time when another parallel brain was moving towards our own, with the potential energy between the brains acting as the inflaton. The end of inflation, in this picture, is the cataclysmic and universe-creating collision of the two brains. This is a beautiful and highly speculative idea, and it is one that can also lead to unique and potentially observable signatures, like the production of cosmic strings, one-dimensional defects in space-time that could be detected through their gravitational lensing effects. This proliferation of different inflationary models has been criticized by some as a sign of the theory's weakness. If the theory is so flexible that it can accommodate almost any new observational result, is it truly a predictive scientific theory? This is a valid and important critique, but it is also a sign of the theory's richness and its deep connection to the most fundamental questions of theoretical physics. The period of inflation is a unique and powerful laboratory, a window onto the physics of the universe at energies that are far beyond the reach of any terrestrial experiment. The subtle patterns in the ancient light of the cosmic microwave background are the fossils of this primordial epoch, and by studying them with ever-increasing precision, we are not just testing the general idea of inflation, we are also, in a very real sense, doing experimental particle physics at the highest possible energies. We are probing the nature of the quantum fields that governed the first moments of creation, and we are searching for the subtle clues that will point us towards a deeper, more unified, and more complete understanding of the fundamental laws of nature. The cosmic microwave background radiation is more than just a beautiful baby picture of our universe. It is a rich and detailed scientific document, a Rosetta Stone that has allowed us to decipher the fundamental parameters of our cosmos with an accuracy that was unimaginable just a few decades ago. The CMB is a perfect blackbody radiator, and the overall shape of its energy spectrum, as measured with incredible precision by the COBE satellite in the early 1990s, is a stunning confirmation of the hot Big Bang model. But the true scientific treasure of the CMB lies in its tiny anisotropies, the 1 part in 100,000 temperature fluctuations that are imprinted on this otherwise uniform glow. These fluctuations are a direct fossil of the primordial density variations that were present in the universe when it was just 380,000 years old. And they are the seeds from which all the large-scale structure in our universe, the galaxies, the clusters, the cosmic web has grown, the statistical properties of these fluctuations, and in particular their angular power spectrum, a plot of how their amplitude varies with their size on the sky, is an incredibly powerful cosmological tool. This power spectrum is not a smooth curve. It has a series of characteristic acoustic peaks. These peaks are the frozen signature of sound waves that were propagating through the hot, dense, primordial plasma of the early universe. Before recombination, the universe was a soup of protons, electrons, and photons, all tightly coupled together. A region of slightly higher density, created by the primordial inflationary fluctuations, would have a stronger gravitational pull, and it would begin to collapse. But as it collapsed, the pressure of the trapped photons would push back, causing the region to expand and to rarefy. This would then reduce the photon pressure, allowing gravity to take over again. And the region would begin to collapse once more. This cycle of gravitational collapse and pressure-driven expansion created a series of oscillating sound waves that rippled through the primordial plasma. The acoustic peaks in the CMB power spectrum correspond to the specific, resonant frequencies of these sound waves. The modes that happen to be at their point of maximum compression or maximum rarefaction at the precise moment of recombination, when the universe became transparent and the photons were released. By precisely measuring the positions and the heights of these peaks, we can extract a wealth of information about the fundamental parameters of our universe. The angular scale of the first and largest peak, for example, is a direct measure of the overall geometry of the universe. The fact that this peak is observed at an angular scale of about 1 degree is the primary evidence that our universe is geometrically flat. The relative heights of the odd and the even peaks tell us about the density of baryonic matter in the universe. And the overall shape of the power spectrum, particularly at small angular scales, is a sensitive probe of the amount of dark matter in the universe. The detailed all-sky maps of the CMB, created by the WMAP and the Planck satellites, have allowed us to measure these acoustic peaks with a precision of a few percent, and in doing so, to determine the fundamental parameters of our standard cosmological model, the Lambda CDM model, with an accuracy that is the envy of many other fields of science. We now know, with high confidence, that our universe is about 13.8 billion years old, that it is geometrically flat, and that it is composed of about 5% normal matter, 27% dark matter, and 68% dark energy. This is a monumental achievement, a testament to the power of modern and precision cosmology. And it is a story that is written in the subtle and beautiful language of sound waves, in the faint, ancient, and ever-present light of the cosmic microwave background. The theory of cosmic inflation is not the only idea that has been proposed to explain the origin of the large-scale structure we see in the universe. While it is the leading and most well-supported paradigm, it is not without its challenges and its critics, and this has spurred the development of a number of interesting and often radical alternative theories. One of the most long-standing of these alternatives is the idea of cosmic strings and other topological defects. In this picture, the early universe, as it cooled after the Big Bang, went through a series of phase transitions, similar to the way that water freezes into ice. These phase transitions, which are predicted by many theories of high-energy particle physics, could have left behind a network of defects, like the cracks that can form in a block of ice as it freezes. Cosmic strings are one-dimensional, line-like defects, incredibly thin, but with an immense energy density. In the 1980s, it was thought that these strings, as they whipped through the early universe at nearly the speed of light, could have acted as the gravitational seeds for galaxy formation. This was a very compelling and elegant idea, as it provided a natural link between particle physics and cosmology. However, the detailed observations of the cosmic microwave background from the COBE and WMAP satellites showed a pattern of fluctuations that was not consistent with the predictions of the cosmic string model. The fluctuations were too Gaussian, too random, to have been produced by the sharp linear features of a network of strings. This led most of the cosmological community to abandon the cosmic string model as the primary source of cosmic structure, and to embrace the inflationary paradigm instead. But this does not mean that cosmic strings do not exist. They could still be out there as a subdominant component of the universe, and astronomers are still actively searching for their subtle gravitational lensing signatures. Another, more recent, and more radical alternative to inflation is the ekpyrotic or cyclic universe model, which we have discussed. In this picture, the hot, dense state of the Big Bang is not the beginning of time, but is the result of a collision between two parallel branes in a higher dimensional space. The density fluctuations that seed the formation of galaxies are not generated by the quantum fluctuations of an inflaton field during a period of exponential expansion, but are generated by quantum fluctuations before the brane collision, during a long, slow period of contraction. These fluctuations are then converted into the familiar scale-invariant density perturbations during the collision itself. This is a very different physical mechanism from inflation, and it makes a number of subtly different and potentially testable predictions. For example, the simplest ekpyrotic models predict a complete absence of primordial gravitational waves, a prediction that is in stark contrast to that of many inflationary models. The search for the B-mode polarization in the CMB is, therefore, a crucial test that can distinguish between these two very different pictures of our cosmic origins. A third class of alternatives attempts to solve the puzzles of the Big Bang without invoking any new, high-energy physics in the early universe. These models often involve a modification to the laws of gravity on very large scales, or the existence of a pre-Big Bang phase where the universe was in a different, and perhaps static or contracting, state. These are often more difficult to reconcile with the full range of cosmological data, but they are an important part of the theoretical landscape, a reminder that we should not become too dogmatically attached to a single paradigm. The ongoing dialogue between the standard inflationary model and these alternative theories is a healthy and essential part of the scientific process. It is a dialogue that pushes us to refine our theories, to sharpen our predictions, and to devise new and more powerful observational tests. The universe is a deep and complex place, and it is entirely possible that the true story of our cosmic origins is one that we have not yet even imagined. The search for this story is a grand human adventure, and it is an adventure that is still, in many ways, just beginning. The legacy of the BICEP-2 experiment, with its dramatic announcement of the detection of primordial gravitational waves in 2014, and its subsequent, and equally dramatic, retraction, is a powerful and important story about the nature of the scientific process. It is a story of bold ambition, of incredible technological achievement, of the excitement of a potential paradigm-shifting discovery, and also of the crucial, and sometimes painful, role of scientific skepticism, of peer review, and of the self-correcting nature of science. The BICEP-2 experiment was a specially designed telescope at the South Pole, built for a single, audacious purpose to detect the faint, swirling, B-mode polarization pattern in the cosmic microwave background that would be the smoking gun signature of cosmic inflation. The team, after years of painstaking work and careful analysis, announced that they had detected just such a signal, at a level that was surprisingly strong, but which was consistent with some of the simplest and most elegant models of inflation. The announcement was met with a wave of global excitement. It was hailed as a discovery of Nobel Prize-winning caliber, a direct observational window onto the first, fleeting moments of the universe's existence. But almost immediately, a number of other cosmologists began to raise questions. The signal was very strong, much stronger than many had expected. And there was another, more mundane, potential source for a B-mode polarization signal, the emission from interstellar dust within our own Milky Way galaxy. The dust grains in our galaxy are not spherical, and they can be aligned by the galaxy's magnetic field. This means that the thermal, microwave radiation that they emit is partially polarized, and this polarized emission can have a swirling B-mode component. The BICEP-2 team had attempted to account for this dust contamination using the best available models at the time, but the crucial piece of information they were missing was a detailed, all-sky map of the polarized dust emission at their specific observing frequency. And that map was about to be released by the European Space Agency's Planck satellite. A few months after the BICEP-2 announcement, a joint analysis of the BICEP-2 and the Planck data was published. And the conclusion was unambiguous. The signal that BICEP-2 had detected was not from primordial gravitational waves. It was almost entirely consistent with being from the polarized emission from galactic dust. The dramatic discovery was, in fact, a dramatic mistake. The story of BICEP-2 is not a story of scientific fraud or incompetence. It is a story of a talented and dedicated team of scientists who were pushing the very limits of their instruments, who were working in a new and largely unexplored area of observational cosmology, and who, in their excitement, made a premature and ultimately incorrect interpretation of their data. And it is a story that, in the end, is a beautiful demonstration of how science is supposed to work. The initial claim was met not with blind acceptance, but with a healthy and rigorous skepticism. Other scientists questioned the analysis. They proposed alternative explanations. They demanded more data. And when that new data became available, the original claim was re-evaluated and ultimately corrected. This is the self-correcting nature of science at its very best. And the story is far from over. The BICEP-2 experiment, and the controversy that it generated has spurred a new, and even more intense, global effort to search for the primordial B-modes. A new generation of more sensitive experiments, both at the South Pole and in other parts of the world, are now collecting data, and they are doing so with a much deeper and more sophisticated understanding of the complex, and often confusing, nature of the galactic dust foregrounds. The legacy of BICEP 2 is not one of failure, but one of progress. It was a bold and ultimately unsuccessful first attempt to open a new window onto the cosmos, and in its failure, it has taught us invaluable lessons that will be essential for the ultimate success of this grand and historic quest. The primordial gravitational waves are still out there, waiting to be discovered, and when they are finally and definitively detected, it will be a triumph that is built on the foundations, both the successes and the failures, of the pioneering work of experiments like BICEP 2. The cosmic web, the vast and beautiful large-scale structure of our universe, with its intricate network of filaments, walls, and voids, is the most magnificent and most direct fossil of the inflationary epoch. The theory of cosmic inflation, as we have seen, provides a natural and elegant mechanism for generating the initial primordial density fluctuations that were the seeds of all this structure. In the first, fleeting moments of time, the inherent quantum uncertainty of the inflaton field created a landscape of tiny microscopic ripples in the energy density of the universe. The period of exponential inflationary expansion then took these microscopic quantum ripples and stretched them to astronomical proportions, imprinting them onto the very fabric of space-time. When the inflationary phase ended, these energy fluctuations were converted into density fluctuations in the hot primordial soup of matter and radiation. These were the seeds of creation. The regions of slightly higher density had a slightly stronger gravitational pull, and they began, over the vast sweep of cosmic time, to attract the matter from their surroundings. The regions of slightly lower density, on the other hand, were gradually evacuated, their matter flowing towards the growing high-density regions. This is the process of gravitational instability, the simple and powerful mechanism by which a nearly uniform or primordial universe can, over billions of years, evolve into the rich and complex tapestry of structures that we see today. The dark matter, with its mysterious non-interacting nature, played a crucial and leading role in this process. The normal, baryonic matter of the early universe was tightly coupled to the photons of the cosmic microwave background, and the intense pressure of this radiation prevented it from collapsing under gravity. But the dark matter, which does not interact with light, felt no such pressure. It was free to begin collapsing into the primordial density wells as soon as the universe became matter-dominated. It formed the invisible gravitational scaffolding, the deep dark matter halos into which the normal baryonic gas would later fall, cool, and form the first stars and galaxies. The large-scale structure of the cosmic web is, in this sense, a direct map of the underlying invisible distribution of dark matter. The bright filaments of galaxies are simply the places where the density of dark matter is highest. The vast dark voids are the places where it is lowest. The statistical properties of this cosmic web, the size of the voids, the thickness of the filaments, the clustering of the galaxies, are all a direct and predictable consequence of the statistical properties of the primordial inflationary fluctuations. And the agreement between the predictions of the inflationary model and the detailed three-dimensional maps of the universe that we have now created, through vast galaxy redshift surveys like the Sloan Digital Sky Survey, is another one of the great triumphs of modern cosmology. We can now, with the aid of powerful supercomputer simulations, take the initial conditions as measured in the cosmic microwave background, the baby picture of the universe at 380,000 years old, and we can evolve that universe forward in time, using only the known laws of gravity and physics, and we can produce a simulated universe that looks, in a statistical sense, almost identical to the real universe we observe around us. This is a monumental achievement. It is a direct and unbroken chain of understanding that connects the quantum fluctuations of the first, infinitesimal fraction of a second of the universe's existence to the formation of our own Milky Way galaxy. Some 10 billion years later, it is a story of incredible scope, of beautiful coherence, and of profound explanatory power. And it is a story that tells us that we are not just living in the universe. We are a part of its deepest and most ancient structure. The atoms in our bodies, the planet we live on, the galaxy we inhabit, are all the direct and beautiful consequence of the simple and yet profound process of gravitational instability, acting on the faint, primordial, and quantum mechanical seeds that were planted at the very dawn of time. The concept of the inflationary bubble, the idea that our entire observable universe is just a small, and perhaps insignificant, patch of a much larger, and possibly infinite, cosmic reality, is one of the most profound and mind-altering implications of the theory of cosmic inflation. This idea arises naturally from the dynamics of the inflationary process itself. The period of exponential expansion is so incredibly rapid and so incredibly powerful that it can take a region of space that was initially infinitesimally small and stretch it to a size that is vastly larger than our current observable horizon. This means that the universe that was created in the Big Bang is, in all likelihood, much, much bigger than the part of it that we can see. The homogeneity and the flatness that we observe within our own local cosmic bubble are not necessarily properties of the entire global universe. They are simply the properties of our own inflated patch. This has a number of fascinating and testable consequences. If our universe is just one inflated bubble, then it is possible that there could be other similar bubbles out there, far beyond our horizon. This is the level Y multiverse, a simple and almost unavoidable consequence of an infinite space and a finite period of inflation. But the concept of the inflationary bubble becomes even more radical in the context of eternal inflation. In this scenario, the process of inflation is a self-reproducing one, with new bubble universes constantly being born from the eternally inflating quantum vacuum. Our own inflationary bubble is just one of an infinite number of other bubbles in a vast cosmic multiverse. And these other bubbles may not be like our own. They could have different physical laws, different constants of nature, different numbers of dimensions. This is a vision of reality that is almost impossibly vast and diverse. And it is a vision that provides a potential and deeply compelling explanation for the apparent fine-tuning of our own universe. But the inflationary bubble is not just a concept that is relevant to the very large scales of the cosmos. It also has a profound connection to the very small scales of quantum mechanics. The primordial density fluctuations that were the seeds of all cosmic structure are in this picture. The quantum fluctuations of the inflaton field, frozen into the fabric of space-time as they were stretched beyond the horizon during the inflationary expansion. These fluctuations are, in a sense, a direct macroscopic manifestation of the inherent uncertainty of the quantum world. The specific pattern of hot and cold spots that we see in the cosmic microwave background is the result of a single, specific and random realization of this quantum process. In a different inflationary bubble, the specific pattern of these quantum fluctuations would be different, leading to a different, specific arrangement of galaxies and clusters. This is a deep and beautiful connection. It tells us that the very structure of our universe, the placement of the galaxies, the shape of the cosmic web, is a fossil, a relic of a single, cosmic scale quantum measurement that took place in the first moments of time. The inflationary bubble is a concept that bridges the gap between the quantum and the cosmos, between the probabilistic world of the very small and the grand, deterministic-looking evolution of the very large. It is a concept that is at the very heart of our modern scientific creation story. A story that is as profound, as beautiful, and as mysterious as any of the ancient myths that it has replaced. The theory of cosmic inflation is not just a story about the past, it is also a story about the future. The same fundamental physics that governed the first and fleeting moments of the universe's existence may also be the key to understanding its ultimate, and perhaps eternal, destiny. The connection between inflation and the future of the cosmos lies in the mysterious and powerful nature of dark energy, the enigmatic force that is currently driving the accelerated expansion of our universe. As we have seen, the leading and most natural candidate for dark energy is the energy of the quantum vacuum itself. And the energy of the quantum vacuum is also the leading and most natural candidate for the energy that drove the period of cosmic inflation. It is a tantalizing and beautiful idea that the same fundamental form of energy is responsible for both the primordial, inflationary burst that created our universe and the gentle, but inexorable, cosmic acceleration that is shaping its future. In this picture, our universe has had two distinct periods of accelerated expansion. The first, inflation, was an incredibly brief, but incredibly violent period, driven by the very high energy density of a false vacuum state. The second, the current era of dark energy domination, is a much more gentle and much more long-lived period, driven by the much lower energy density of our current true vacuum state. This raises a profound and difficult question: why are these two energy scales so vastly different? The energy density of the inflationary vacuum was at least 60 orders of magnitude larger than the energy density of the dark energy vacuum we observe today. This is another, and perhaps even deeper, version of the fine-tuning problem. Why did the universe, after its period of high-energy inflation, settle into a vacuum state with an energy that is so incredibly, exquisitely small, but not quite zero? A zero vacuum energy would have led to a universe whose expansion was constantly decelerating under the pull of gravity. A slightly larger vacuum energy would have been so powerful that it would have prevented the formation of galaxies and stars. We live in a universe that seems to be balanced on a razor's edge. The theory of eternal inflation and the multiverse, combined with the string theory landscape of 10 to the power of 500 possible vacuum states, provides a potential anthropic explanation for this. Perhaps all of these different vacuum energies are realized in different bubble universes. We simply find ourselves in one of the rare bubbles where the final dark energy vacuum is small enough to allow for a long and interesting cosmic history. But the connection between inflation and dark energy also opens up other, more speculative and more dramatic possibilities for our cosmic future. What if our current vacuum state is not the true final ground state of the universe? What if it is, like the inflationary vacuum of the early universe, a false vacuum, a metastable state that could, one day, decay into an even lower energy state? This is the scenario of vacuum decay. If a bubble of this true vacuum were to spontaneously nucleate somewhere in our universe, it would expand at nearly the speed of light, converting our familiar vacuum into this new and potentially lethal state as it went. The laws of physics, the properties of the particles, the very stability of matter itself could be different inside this bubble. It would be the ultimate and most final of all cosmic disasters, a phase transition that would literally erase our universe from existence. This is a terrifying but physically plausible possibility. And it is a possibility that is deeply connected to the physics of inflation. The same quantum tunneling processes that may have allowed our universe to begin in a false vacuum state could also, one day, bring it to an end. The story of inflation, then, is a story that is not just about our ultimate origins, but also about our ultimate fate. It is a story that is written in the subtle and still mysterious properties of the quantum vacuum. A story that reminds us that we live in a universe that is not just expanding, but is also, in the deepest sense, a work in progress, a dynamic, evolving, and perhaps, ultimately, an unstable cosmic experiment. The isotropy of our universe, the fact that it looks the same in all directions on large scales, is one of the most fundamental and most well-established of all cosmological observations. It is a cornerstone of the cosmological principle, the idea that we do not occupy a special or privileged position in the cosmos, and it is a property that is beautifully and naturally explained by the theory of cosmic inflation. The inflationary paradigm, with its period of hyper-accelerated expansion, takes a tiny, causally connected, and therefore smooth and isotropic, patch of the primordial universe and stretches it to a size that is vastly larger than our current observable horizon. This ensures that the universe we see today, within our own local cosmic bubble, is, for all practical purposes, perfectly isotropic. But what if this isotropy is not perfect? What if there are subtle, and as yet undetected, deviations from this perfect statistical uniformity? The search for these anisotropies is one of the most exciting and promising frontiers in modern observational cosmology. And it is a search that could provide us with a new and incredibly powerful window onto the physics of the very early universe, and even, perhaps, with the first tantalizing hints of a reality that lies beyond our own. Single universe. Some of the more complex models of inflation, for example, predict the existence of subtle and specific forms of statistical anisotropy in the cosmic microwave background. A model with two or more interacting inflaton fields, for example, could leave a faint but detectable imprint on the CMB, a slight preference for fluctuations of a certain shape or orientation. The search for these non-Gaussian signatures in the high-precision maps of the CMB from the Planck satellite is an active and ongoing area of research. A confirmed detection of non-Gaussianity would be a revolutionary discovery. It would rule out the simplest single-field models of inflation and would provide us with a direct observational probe of the complex multi-field dynamics of the primordial universe, another and even more spectacular potential source of anisotropy would be a collision with another bubble universe in the context of the multiverse. If our own inflationary bubble had, in its distant past, collided with another, it would have left a cosmic bruise on our sky, a large circular region of the CMB with a slightly different temperature or polarization. The search for these bubble collision signatures is a high-risk, high-reward endeavor. A confirmed detection would be the first, direct, and unambiguous evidence for the existence of the multiverse, a discovery that would forever change our understanding of our place in the cosmos. Even in the absence of such dramatic primordial signatures, the large-scale structure of the universe that we see today is not perfectly isotropic. The cosmic web, with its filaments and voids, is a testament to this. And on the very largest observable scales, there are some intriguing, and as yet unexplained, hints of a large-scale flow or tilt in the universe, a slight preference for the motion of galaxy clusters in a particular direction. A dark flow. This could be a statistical fluke, a result of the fact that we are only seeing a small and perhaps unrepresentative patch of a much larger and truly isotropic universe. But it could also be a sign of something much deeper, the gravitational influence of a vast, and as yet unseen, concentration of mass that lies beyond our cosmic horizon, a remnant of a large-scale anisotropy in the primordial inflationary field. The quest to understand the isotropy of our universe and the subtle and potentially profound deviations from it is a quest that is pushing the very limits of our observational capabilities and our theoretical imagination. It is a quest that reminds us that even the most well-established of our scientific principles should be constantly tested, questioned, and probed. For it is often in the small and seemingly insignificant cracks in the facade of our established theories that the first, faint light of a new and more complete understanding of the universe begins to shine. The scientific journey to understand our cosmic origins is a story of a constant and creative dialogue between theory and observation. A bold new theoretical idea, like cosmic inflation, makes a set of specific, testable predictions. A new generation of powerful observational instruments is then built to test these predictions with ever-increasing precision. The results of these observations can either confirm the theory, forcing us to refine and to deepen it, or they can falsify it, sending the theorists back to their blackboards to search for a new and better idea. This is the beautiful, self-correcting, and endlessly progressive nature of the scientific method. And in the field of cosmology, this dialogue is currently playing out in a number of exciting and crucial arenas. The search for the primordial. B-mode polarization in the cosmic microwave background is perhaps the most important and most direct of these tests. A definitive detection of this faint, swirling signal would be a triumphant confirmation of the inflationary paradigm and a direct window onto the physics of the universe's first moments. But a definitive non-detection, would be just as profound. If, after a new generation of even more sensitive experiments, we still see no sign of these primordial gravitational waves, it would place incredibly tight constraints on a large class of inflationary models, and it might even force us to abandon the simplest single-field models altogether, pushing us towards more exotic alternatives, like the ekpyrotic or the cyclic universe models, which predict a complete absence of these waves. The precise measurement of the statistical properties of the density fluctuations in the CMB and in the large-scale structure of galaxies is another crucial testing ground. The simplest models of inflation predict a power spectrum of fluctuations that is almost, but not quite, scale invariant, and that is almost, but not quite, perfectly Gaussian. The search for tiny deviations from this simple, vanilla picture, a running of the spectral index, a hint of non-Gaussianity, a subtle, statistical anisotropy is a major focus of modern precision cosmology. Any confirmed detection of such a deviation would be a revolutionary discovery, a direct clue to the more complex, and more interesting, physics that was at play during the inflationary epoch. Computer simulations are another essential tool in this dialogue between theory and observation. A modern cosmological simulation is a universe in a box, a vast computational experiment that allows us to take the initial conditions as predicted by a particular inflationary model and to evolve them forward in time, using the known laws of gravity and physics to see what kind of universe they produce. We can then compare the statistical properties of this simulated universe, the properties of its galaxies, its clusters, its cosmic web with the properties of the real universe we observe. This allows us to rule out certain models, to refine others, and to gain a deeper, more intuitive understanding of the complex, nonlinear processes that connect the simple, primordial universe with the rich and complex cosmos we see today. And finally, there is the ever-present possibility of a complete surprise, of a black swan discovery that comes out of left field and forces us to rethink everything. The discovery of dark energy was just such a surprise, and there may be others lurking in the vast and still largely unexplored datasets from our new generation of telescopes. Perhaps we will find a new, unexpected particle in the data from the Large Hadron Collider. Perhaps we will find a fundamental inconsistency in the laws of gravity by observing the motions of stars around the supermassive black hole at the center of our galaxy. The history of science is a history of such surprises, and it is a history that is far from over. The dialogue between theory and observation, between our creative, imaginative models of the universe and the hard, empirical, and often surprising facts that the universe reveals to us, is a dialogue that is at the very heart of the scientific enterprise. It is a dialogue that has, in the last century, given us a story of our cosmic origins that is more profound, more beautiful, and more wondrous than any of our ancient myths. And it is a dialogue that is poised, in the coming years and decades, to lead us to an even deeper and more complete understanding of our place in the grand and ever-unfolding cosmic story. The future of our quest to understand the universe and our own inflationary origins is a future that is bright with the promise of new and even more powerful observational tools. We are living in a golden age of cosmology, an age where our technological capabilities are, for the first time, beginning to match the scale of our deepest and most ambitious scientific questions. In the coming decade, a new generation of ground-based and space-based observatories will come online, and they will provide us with a flood of new, high-precision data that will allow us to test the theory of cosmic inflation and its alternatives with an unprecedented level of rigor. The search for the primordial, B-mode polarization in the cosmic microwave background will be a major focus of this effort. A new Stage 4 CMB experiment, a vast array of telescopes at the South Pole and in the high Atacama Desert of Chile, will map the polarization of the CMB with a sensitivity that is an order of magnitude greater than any previous experiment. This may be our best, and perhaps our final, chance to detect the faint, swirling signature of the gravitational waves from the very beginning of time. In space, the European Space Agency's Euclid mission and the Vera C. Rubin Observatory in Chile will create the largest and most detailed three-dimensional maps of the universe ever made. By measuring the positions and the shapes of billions of galaxies, these surveys will allow us to trace the growth of cosmic structure over the last 10 billion years of cosmic history. This will provide a powerful and completely independent test of the inflationary paradigm. We will be able to compare the statistical properties of the final cosmic web with the statistical properties of the initial seeds as seen in the CMB, a direct and powerful test of our entire gravitational instability model of structure formation. The detection of gravitational waves from other astrophysical sources is also opening a new and revolutionary window onto the cosmos. The current ground-based network of LIGO and Virgo detectors is constantly being upgraded, increasing its sensitivity and its reach. And in the 2030s, the Laser Interferometer Space Antenna will take this new science into space. LISA will be sensitive to the much lower frequency gravitational waves that are emitted by the mergers of supermassive black holes in the centers of distant galaxies. And it may also have the sensitivity to detect the faint, stochastic hum of the gravitational wave background from the Big Bang itself, a direct and pristine signal from the very first moments of the universe's existence. The James Webb Space Telescope will continue to push our observational frontier ever closer to the beginning of time, searching for the very first galaxies to light up the cosmos. And a new generation of powerful, ground-based, 30-meter class telescopes will provide the crucial high-resolution spectroscopic follow-up that will be needed to understand the physics of these first luminous objects. On the theoretical front, the quest for a unified theory of quantum gravity will continue, guided and constrained by these new, high-precision observational data. And the rapid development of quantum computers may one day provide us with a completely new tool for exploring the mysteries of the early universe. a tool that will allow us to simulate the complex quantum dynamics of space-time itself, a simulation that is far beyond the reach of any classical computer. The future of cosmology is a future of synergy, of integration, of a multi-messenger approach that will combine the information from all of these different windows onto the cosmos, the light, the gravitational waves, the neutrinos, to create a single, coherent, and deeply nuanced picture of our universe, from its first inflationary moments to its ultimate, and still mysterious, fate. We are living in a remarkable and privileged time, a time when the deepest and most ancient of all human questions, the questions of our own cosmic origins, are finally beginning to come within the reach of our scientific understanding. The journey is far from over, but the path ahead is bright with the promise of discovery. The ultimate fate of our universe, the final chapter in the grand cosmic story, is a topic that has long been a source of fascination, of speculation, and of a certain existential awe. And it is a topic that is intimately and inextricably linked to the physics of the very early universe, to the process of cosmic inflation, and to the mysterious and powerful nature of dark energy. The standard and most plausible scenario for our cosmic future, based on our current best understanding of the data, is that of a big freeze or a heat death. In this picture, the dark energy that is driving the accelerated expansion of the universe is a cosmological constant, an intrinsic and unchanging energy of the vacuum itself. If this is the case, then the universe will continue to expand at an ever-increasing rate, forever. The consequences of this eternal expansion are profound, and ultimately bleak. As the universe expands, the density of matter and radiation will continue to decrease, while the density of dark energy remains constant. This means that dark energy will become more and more dominant over time. The galaxies in our own local gravitationally bound supercluster will eventually merge into a single, vast supergalaxy. But all the other galaxies in the universe will recede from us at an ever-increasing speed, eventually crossing our event horizon and disappearing from our view. The night sky of the far future will be a dark, empty, and lonely place. Within our own isolated supergalaxy, the process of star formation will gradually come to a halt as the reservoirs of cold, dense gas are used up. The existing stars will one by one exhaust their nuclear fuel, the smaller, sun-like stars fading into cold, dark white dwarfs, and the more massive stars collapsing into neutron stars or black holes. The universe will become a graveyard of stellar remnants. Over much, much longer timescales, even these remnants will begin to decay. The white dwarfs and neutron stars will slowly evaporate through a process of proton decay. If such a process is allowed by a grand unified theory, and the black holes, the most stable of all objects, will slowly but inexorably evaporate through the process of Hawking radiation. After an almost unimaginable amount of time, a googol years or more, the universe will be a cold, dark, and almost perfectly empty void, a thin, featureless soup of photons, neutrinos, and a few stray elementary particles, a state of maximum entropy, a state of final and eternal heat, death. This is a cold and sobering vision of our ultimate cosmic destiny. But it is not the only possibility. If the dark energy is not a cosmological constant, but a more dynamic quintessence field, then its properties could change over time. It is possible that the quintessence field could, in the far future, decay, causing the cosmic acceleration to slow down, to stop, and perhaps even to reverse, leading to a big crunch, a final, fiery collapse of the universe back into a singularity. Or, in a more exotic and more terrifying scenario, The dark energy could be a form of phantom energy, a field whose energy density increases as the universe expands. This would lead to a big rip. In the final moments of such a universe, the repulsive force of the phantom energy would become so strong that it would overcome all the other forces of nature. It would tear apart the galaxy clusters, then the galaxies, then the solar systems, then the planets, and in the final, fleeting instant, it would even tear apart the atoms and the atomic nuclei themselves, ripping the very fabric of space-time into an infinite number of causally disconnected pieces. The physics of cosmic inflation is deeply connected to all of these future scenarios. The specific model of inflation that describes our own early universe determines the initial conditions from which the rest of cosmic history unfolds, and the nature of the inflaton field itself may be a clue to the nature of the dark energy field that is shaping our future. It is a beautiful and deeply profound symmetry that the same fundamental physics that governed the first fleeting moments of our universe's birth may also be the physics that will dictate its ultimate, and perhaps eternal, fate. The relationship between the theory of cosmic inflation and the grand philosophical questions of our origins, our purpose, and our ultimate destiny is a deep and multifaceted one. Inflation is not just a scientific theory. It is a new and profoundly humbling creation story for a modern scientific age. It is a story that has, in many ways, replaced the older, more anthropocentric stories of our religious and mythological traditions. But it is a story that is no less wondrous, no less beautiful, and no less capable of inspiring a sense of awe and reverence for the cosmos. The inflationary paradigm, with its vision of a universe born from a tiny quantum fluctuation in a primordial vacuum, is a story that places our own to human existence in a new and radically different cosmic perspective. It tells us that we are the children of chance, the fortunate and perhaps improbable outcome of a random quantum process at the beginning of time. This is a vision that can be seen as profoundly disenchanting by some, as it seems to remove any sense of a preordained purpose or a divine plan from the cosmos. But it can also be seen as profoundly liberating. If our existence is not the fulfillment of some external purpose, then we are free to create our own meaning, to define our own values, to write our own human story on the vast and otherwise silent canvas of the cosmos. The theory of eternal inflation and the multiverse that it implies takes this sense of cosmic contingency to its ultimate conclusion. If our universe is just one of an infinite number of other parallel realities, each with its own different physical laws, then our own local cosmic home is not just an accident. It is an accident of an almost unimaginable scale. And yet, this vision of a vast and perhaps infinitely diverse multiverse can also be a source of a new kind of cosmic connection, a new kind of cosmic pluralism. It suggests that the principles of creativity, of complexity, of emergence are not unique to our own universe, but are likely to be a common and perhaps universal feature of reality. It invites us to see our own human story not as the only story, but as one of many, a single, beautiful note in an infinite and eternal cosmic symphony. The theory of inflation is also a story about the deep and beautiful connection between the very small and the very large. It tells us that the grand macroscopic structure of our universe, the galaxies, the clusters, the cosmic web, is a direct and fossilized imprint of the quantum fluctuations of the first infinitesimal moments of time. This is a profound and deeply holistic vision of the cosmos. It tells us that the universe is not a collection of separate, disconnected parts, but a single, unified, and co-evolving whole. And we are an integral part of this whole. The atoms in our bodies, The consciousness in our minds are a direct and unbroken continuation of the same creative process that began in the inflationary fire of the Big Bang. This is a vision of our place in the universe that is not based on a sense of a privileged, central position, but on a sense of a deep and deeply humbling participation. We are not the masters of the universe. We are the universe, having become aware of itself. And as we continue to probe the mysteries of our own inflationary origins, with our new and ever more powerful tools of science, we are not just collecting data about the past. We are, in a very real sense, deepening our own self-awareness as a cosmic species. We are piecing together the long, strange, and beautiful story of our own cosmic journey. A journey that has taken us from the quantum foam of the primordial void to the threshold of a new, and perhaps boundless, future. The future of our quest to understand the universe and our own inflationary origins is a future that is bright with the promise of new and even more powerful observational tools. We are living in a golden age of cosmology, an age where our technological capabilities are, for the first time, beginning to match the scale of our deepest and most ambitious scientific questions. In the coming decade, a new generation of ground-based and space-based observatories will come online, and they will provide us with a flood of new, high-precision data that will allow us to test the theory of cosmic inflation and its alternatives with an unprecedented level of rigor. The search for the primordial. B-mode polarization in the cosmic microwave background will be a major focus of this effort. A new Stage 4 CMB experiment, a vast array of telescopes at the South Pole and in the high Atacama Desert of Chile, will map the polarization of the CMB with a sensitivity that is an order of magnitude greater than any previous experiment. This may be our best, and perhaps our final, chance to detect the faint, swirling signature of the gravitational waves from the very beginning of time. In space, the European Space Agency's Euclid mission and the Vera-C Rubin Observatory in Chile will create the largest and most detailed three-dimensional maps of the universe ever made. By measuring the positions and the shapes of billions of galaxies, these surveys will allow us to trace the growth of cosmic structure over the last 10 billion years of cosmic history. This will provide a powerful and completely independent test of the inflationary paradigm. We will be able to compare the statistical properties of the final cosmic web with the statistical properties of the initial seeds as seen in the CMB, a direct and powerful test of our entire gravitational instability model of structure formation. The detection of gravitational waves from other astrophysical sources is also opening a new and revolutionary window onto the cosmos. The current, ground-based network of LIGO and Virgo detectors is constantly being upgraded, increasing its sensitivity and its reach. And in the 2030s, the Laser Interferometer Space Antenna will take this new science into space. LISA will be sensitive to the much lower frequency gravitational waves that are emitted by the mergers of supermassive black holes in the centers of distant galaxies. And it may also have the sensitivity to detect the faint, stochastic hum of the gravitational wave background from the Big Bang itself, a direct and pristine signal from the very first moments of the universe's existence. The James Webb Space Telescope will continue to push our observational frontier ever closer to the beginning of time, searching for the very first galaxies to light up the cosmos. And a new generation of powerful, ground-based 30-meter class telescopes will provide the crucial high-resolution spectroscopic follow-up that will be needed to understand the physics of these first luminous objects. On the theoretical front, the quest for a unified theory of quantum gravity will continue, guided and constrained by these new high-precision observational data. And the rapid development of quantum computers may one day provide us with a completely new tool for exploring the mysteries of the early universe. a tool that will allow us to simulate the complex quantum dynamics of space-time itself, a simulation that is far beyond the reach of any classical computer. The future of cosmology is a future of synergy, of integration, of a multi-messenger approach that will combine the information from all of these different windows onto the cosmos, the light, the gravitational waves, the neutrinos to create a single, coherent, and deeply nuanced picture of our universe, from its first inflationary moments to its ultimate and still mysterious fate. We are living in a remarkable and privileged time. A time when the deepest and most ancient of all human questions, the questions of our own cosmic origins, are finally beginning to come within the reach of our scientific understanding. The journey is far from over, but the path ahead is bright with the promise of discovery. It should have been a simple test. The wormhole, a shimmering, stable tear in the fabric of space-time, stretched from a quiet orbit around the Moon to a designated empty patch of space near the orbit of Neptune. A welcome party was already in position there, waiting to greet the brave crew who would be the first humans to take a shortcut through the cosmos. The effort to reach this point had been monumental. A multi-generational project that had consumed a significant portion of humanity's resources and scientific talent. It had required us to reach down into the roiling, chaotic sea of the quantum foam, that submicroscopic realm where space-time itself is in a constant state of turmoil, and to pluck a single, nascent wormhole from its depths, carefully nurturing and expanding it to a macroscopic, traversable size. The equations of Einstein's general theory of relativity had predicted the possibility of such structures, these space-time bridges, for centuries. And now, after decades of painstaking work, here it was, a shimmering, spherical gateway to the stars. This was not just a scientific experiment. It was the culmination of a dream, the dream of interstellar travel, of a future where humanity was no longer confined to its cradle, but could finally step out into the vast cosmic ocean. The last calibrations were made, the final checks completed. The ship, a sleek silver vessel named the Pilgrim, and its four-person crew entered the wormhole's throat, passing easily through the spherical, shimmering boundary of its entrance. From the observation posts on the Moon, onlookers watched as the ship receded, its form gradually shrinking, appearing to move effortlessly and serenely towards its destination, some 4.12 billion kilometers away. At the other end, near Neptune, the reception party watched on their own screens as the ship began to appear, a small point of light that grew steadily larger as the minutes ticked by. A preliminary unmanned test probe had taken just over 30 minutes to traverse the distance, and the Pilgrim seemed to be on a similar, perfect trajectory. A quiet sense of triumph, of a new era dawning, began to settle in. But then, a subtle shift in the data, a flicker of concern in the mission control centers on both ends of the journey. The ship, which had been steadily growing larger in the viewports of the Neptune reception party, appeared to slow down. Then, it seemed to stall, its image frozen, hanging in the void just beyond the wormhole's exit. 30 minutes passed, the expected arrival time. The ship did not emerge. An hour passed, then a day, then weeks, then months, then years. Time-sensitive, high-precision telescopes, positioned at both the entrance and the exit of the wormhole, were able to confirm that the ship was, in fact, still in motion, but its progress was almost imperceptibly, agonizingly slow. A new and terrifying reality began to dawn. The crew of the Pilgrim was trapped, not in space, but in a strange, distorted, and seemingly endless river of time within the wormhole itself. A frantic and desperate debate raged across the solar system. Should we send a rescue mission? But how could another ship enter the same treacherous passage? Should we try to turn off the massive generators that were feeding the exotic, negative energy required to keep the wormhole stable? But any sudden change to the delicate balance of forces could cause the wormhole to collapse catastrophically, tearing the ship and its crew to pieces. Every option seemed to lead to the same tragic conclusion. The only safe option, the only humane option, was to wait. And so, humanity waited. We watched the frozen image of the ship, a silent monument to our ambition and our hubris, and we waited. 500 years passed before what was left of the Pilgrim finally, slowly, drifted out of the wormhole's exit. It was a ghost ship, a broken, pitted husk, its systems barely functioning, its hull scarred by centuries of exposure to the harsh, and still not fully understood. Conditions within the wormhole's throat. The crew, of course, was long dead. Their skeletal remains still strapped into their command chairs, a silent, eternal testament to a dream that had turned into a nightmare. Only then, after the last of the wreckage had been recovered, was the wormhole finally and permanently shut down. We had miscalculated. The beautiful, elegant equations of general relativity, the machine that had promised us the stars, were not enough. We thought we had understood the complex and treacherous intersection of gravity and quantum mechanics. We thought we had accounted for every possible interaction, every subtle nuance of the physics, but some crucial hidden variable, had been missed. Humanity looked out at the distant, glittering stars, and we had never felt more profoundly and more completely alone. The universe had offered us a shortcut, a beautiful and tantalizing promise, and it had turned out to be a trap. The story of wormholes is a story of the power and the peril of a great scientific theory. They are a natural and almost unavoidable consequence of the mathematics of Einstein's general theory of relativity. The idea of them is almost as old as the theory itself, but relativity, for all its beauty and its power, is just a machine. It is a set of rules, a mathematical algorithm. You feed it an input, a particular arrangement of matter and energy, and it gives you an output, a prediction for how space-time will curve, and how matter will move within that curved space-time. The machine does not, and cannot, tell you whether your initial input, your imagined scenario, is something that the universe actually allows. It is up to us, as physicists and as observers of nature, to figure out which of the many possible solutions to Einstein's equations correspond to the real world, and which are mere mathematical fantasies. The story of our ill-fated test pilots is a cautionary tale, a reminder that the path from a beautiful mathematical idea to a physical reality is often a long and treacherous one. So, what would it really take to build a wormhole? What are the physical mechanisms that might allow for their existence, and what are the deep and perhaps insurmountable obstacles that might forbid them? Are they a viable, if distant, hope for our future among the stars, a destination for our dreams? Or are they, as our fictional story suggests, a beautiful but deadly siren's call, a path that leads not to a new world, but to an early and very lonely death? The answers to these questions lie at the very frontiers of our understanding of gravity, of space-time, and of the fundamental nature of reality itself. In the year 1848, just 1 year before his own mysterious and untimely death, The American writer Edgar Allan Poe published a strange and sprawling work of prose that he considered to be his masterpiece. Its title was Eureka. The text is a dense and often confusing mixture of poetry, philosophy, and speculative cosmology, and it is largely ignored today, overshadowed by his more famous and accessible tales of horror and mystery. But buried within this tangled mass of prose, about two-thirds of the way through, in the midst of a rambling discourse on the nature of interstellar space, Poe makes a startling and uncannily prescient declaration. He states, almost as an aside, that space and duration are one. In Poe's poetic and intuitive vision, the three dimensions of space and the single dimension of time were not separate entities, but were somehow unified, two aspects of a single underlying reality. Nearly a century later, a young physicist named Albert Einstein, working in a patent office in Bern, Switzerland, had no idea that he was, in a sense, echoing the strange and beautiful intuition of a long-dead New England poet. The year was 1905, a year that would go down in the annals of science as Einstein's Annus Mirabilis, his year of miracles. In that single, remarkable year, he published a series of papers that would revolutionize our understanding of the physical world. And in one of those papers, perhaps his most consequential, he formulated his special theory of relativity. This theory was built on two simple, but radical, postulates that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is a universal constant, the same for all observers, regardless of their own motion. The consequences of these two simple ideas were profound. They showed that measurements of length and time are not absolute, but are relative to the observer. A moving clock ticks more slowly than a stationary one. A moving object appears shorter in its direction of motion. Space and time were no longer the fixed, absolute, and independent entities of Newtonian physics. They were dynamic and intertwined. But it was Einstein's former teacher, the mathematician Hermann Minkowski, who took the final, crucial step. He realized that the strange, counterintuitive effects of special relativity could be understood in a much more natural and elegant way if one abandoned the idea of a three-dimensional space and a separate, one-dimensional time, and instead worked with a single, unified, four-dimensional entity space-time. In Minkowski's geometric formulation, space and time were not identical, as Poe had perhaps imagined, but were different facets of a single, unified reality, two inseparable components of a four-dimensional continuum. Einstein, learning once again from his old teacher, quickly embraced this powerful new idea and used it as the foundation for his next, and even greater, leap of imagination. In 1915, he unleashed upon an unsuspecting world his general theory of relativity. In the new and beautiful language of general relativity, space-time is no longer a passive, static stage upon which the drama of physics unfolds. It is an active participant in the drama. The presence of matter and energy causes the unified fabric of space-time to bend and warp. And in turn, the curvature of space-time tells matter and energy how to move. The great physicist John Archibald Wheeler would later summarize this profound and beautiful idea in a single, elegant phrase. Space-time tells matter how to move. Matter tells space-time how to curve. This is not an abstract, theoretical concept. It is a physical reality that is happening all around you and within you at this very moment. The Earth is not held in its orbit by a mysterious, invisible force of gravity reaching out from the sun. It is simply following the straightest possible path through the curved space-time created by the sun's immense mass. The light from distant stars is bent as it passes by a massive galaxy, a phenomenon known as gravitational lensing, which allows us to use these galaxies as natural cosmic telescopes and as massive, cataclysmic events, like the collision of two black holes, unfold in the distant universe. They send out ripples in the fabric of space-time, gravitational waves that travel across the cosmos at the speed of light. As these waves wash over the Earth, they are constantly, gently stretching and squeezing the very space you are in. The effect is impossibly small, a distortion on the scale of a single atomic nucleus, but it is real. And with our incredibly sensitive gravitational wave detectors, we can now hear the faint, cosmic symphony of these distant, violent events. But the general theory of relativity, like the writings of Poe, is a work of immense beauty, profound depth, and sometimes daunting complexity. It is more than just a simple physical theory of nature. It is a machine. It is a set of 10 tangled, nonlinear, four-dimensional differential equations. You provide the machine with an input, a specific, imagined arrangement of matter and energy, and the machine, after a great deal of mathematical wrangling, will give you an output, a precise mathematical description of the resulting geometry of space-time, and a prediction for how that system will evolve. But the machine is agnostic. It does not tell you whether your initial input is a scenario that is physically possible in our universe. That is a question that you, as a physicist, must decide. This is not a feature unique to relativity. Newton's law of universal gravitation, which relativity replaced, works in the same way. You can, in principle, use Newton's law to calculate the gravitational field of a solid iron rod that is 10,000 light-years long. The equations will dutifully give you an answer. But it is up to you to use your knowledge of the rest of physics, of astrophysics, of material science, to decide whether a 10,000 light-year long solid iron rod is a physically plausible object. The problem is that the equations of general relativity are vastly more complex, and their solutions often describe phenomena that are far outside the realm of our everyday experience, making it much more difficult to use our intuition to separate the physically real from the mathematically possible. The physics community in the early 20th century recognized the profound truth and beauty of Einstein's theory, but its sheer mathematical difficulty was so great that many preferred to work on the more tractable problems of the burgeoning fields of subatomic and astrophysical physics. The pioneering physicist J.J. Thomson once famously remarked, "I have to confess that no one has succeeded in stating in clear language what the theory of Einstein's really is." Despite this daunting complexity, some progress was made in the years immediately following 1915. While serving in the German army on the Russian front during the First World War, the physicist Karl Schwarzschild found the first exact, non-trivial solution to Einstein's equations. He took the machine of relativity and fed it the simplest possible, non-empty input, a single, static, spherically symmetric, non-rotating mass, a mathematical object intended to approximate the gravitational field of a star, like our sun. The machine dutifully churned out an answer, a description of the curved space-time surrounding this mass. The Schwarzschild metric, as it is now known, was a triumph. It accurately described the orbits of the planets in our solar system, and it made new testable predictions, like the bending of starlight, which were later confirmed with stunning precision. But buried deep within Schwarzschild's elegant equations, there was a strange and disturbing feature, a mathematical pathology that seemed to suggest a reality far more bizarre than anything in our solar system. The solution contained a singularity. The equations predicted that if the entire mass of the object were to be squeezed below a certain critical radius, the Schwarzschild radius, then the curvature of spacetime would become infinite at the center, the object's own. Immense gravity would overcome all other forces, and it would collapse into a single, dimensionless point of infinite density. This singularity would be surrounded by a one-way membrane, an event horizon, a point of no return from which nothing, not even light, could escape. The machine of relativity had produced a monster. And now it was up to the physicists to decide if this monster could be real. For decades, the overwhelming consensus was that it could not. Most physicists, including Einstein himself, scoffed at the idea. They believed that the singularity was just a mathematical artifact of the oversimplified, idealized scenario that Schwarzschild had used. In a real physical collapse, they argued, the complex, messy physics of a real star, its rotation, its pressure, its radiation would surely intervene and prevent the formation of such an absurd, infinitely dense point. In a 1939 paper, Einstein himself argued that no real object could ever be compressed to its Schwarzschild radius, that the forces of nature would always win out over the pull of gravity. These hypothetical objects, which were then known as frozen stars, were, in his view, a physical impossibility. But a young American physicist named J. Robert Oppenheimer disagreed, just a few months after Einstein's dismissive paper. Oppenheimer, working with his student Hartland Snyder, was exploring the fate of massive stars. He had just completed a groundbreaking calculation that determined the maximum possible mass of a neutron star, the incredibly dense remnant left behind after a supernova explosion. He then asked a simple but profound question: what happens to a star that is more massive than this limit? What happens when a star is so massive that not even the immense quantum mechanical pressure of densely packed neutrons can hold it up against the relentless crush of its own gravity? Oppenheimer and Snyder took the full known physics of a massive star and fed it into the machine of general relativity. And the answer that came out was the exact opposite of Einstein's. They found that for a sufficiently massive star, there was nothing, absolutely nothing, that could halt the process of gravitational collapse. The star was doomed, and once the collapse began, the machine of relativity told them exactly what would happen. In their landmark paper, they stated their conclusion with a chilling clarity. The star thus tends to close itself off from any communication with a distant observer. Only its gravitational field persists. They had, for the first time, provided a physically realistic mechanism for the formation of a black hole, but their work was published on September 1st, 1939. The very same day that Germany invaded Poland and the Second World War began. The world's attention was, understandably, focused elsewhere. Their paper was largely forgotten for decades. Oppenheimer himself was soon swept up into the immense, world-changing vortex of the Manhattan Project. His brilliant mind diverted from the mysteries of the cosmos to the terrible, practical physics of the atomic bomb. He would never return to the astrophysical questions that had so fascinated him as a young man. But history, and the universe, would eventually vindicate his and Snyder's conclusion. In the decades that followed, through a combination of theoretical advances and new, powerful astronomical observations, it would become indisputable. Black holes were not just a mathematical curiosity of Einstein's equations. They were real, physical objects scattered throughout our universe. The machine of relativity had, once again, been proven right. But was this all that the machine predicted, or were there other, even stranger, monsters lurking in the tangled depths of its equations as Oppenheimer was working away in the deserts of New Mexico? Another brilliant mind, working in the very different, and often perilous, environment of the Soviet Union, had found another, even more bizarre, possibility. He had found the black hole's mirror twin. The Soviet astronomer Igor Novikov was born in Moscow in 1935, and despite the immense challenges of working as a scientist under a politically repressive regime, he quickly rose to become a leading figure in Soviet astrophysics. Little is known of his personal life, but we know that to be a successful physicist in the Soviet Union required a delicate balancing act. Your research could not be seen to conflict with the official dialectical materialist ideology of the state. You were often pulled away from your own interests to work on state-sponsored, high-priority projects. And the Iron Curtain made it incredibly difficult to communicate your work to the wider international scientific community. And yet, within these constraints, Novikov found enough intellectual freedom to pursue some decidedly unorthodox and brilliant lines of research. And in 1964, he had a great revelation, a revelation that was born from a simple but profound insight into the nature of gravity and time. Imagine you take a video of yourself tossing a ball up into the air and then catching it. If you were to play this video in reverse, it would look perfectly natural. The mathematics that describe the ball's motion under the influence of gravity. The laws of Newtonian mechanics are time-symmetric. They do not have a preferred direction of time. The same is true for the much more complex mathematics of Einstein's general relativity. The equations do not, in themselves, distinguish between the past and the future. They are like a mirror that does not know which is the object and which is the reflection. It is up to us, as physicists, to use our knowledge of the rest of the universe, particularly the second law of thermodynamics, the arrow of time, to decide which of the time-symmetric solutions to the equations are physically plausible. Novikov realized that since a black hole is a particular solution to the equations of general relativity, then its time-reversed counterpart must also be a valid mathematical solution. Instead of an object that traps things forever, a black hole, there could be an object that ejects things forever, a white hole. Novikov, and independently, the Israeli physicist Yuval Ne'eman, proposed this idea as a potential explanation for the mysterious, incredibly bright, and distant objects that were then being discovered by astronomers, objects that we now know as quasars. Perhaps these were not distant galaxies, but white holes in our own galaxy, spewing out matter and energy that had been created in the Big Bang. Because of the political and scientific isolation of the Soviet Union, Novikov's work was largely unknown in the West for many years, but the idea was a stunning one. A white hole would be a truly bizarre and paradoxical object, perhaps even stranger than its black hole twin. It would still have a singularity at its center, a point of infinite density. But this singularity would be in the past, not the future. The white hole would be surrounded not by an event horizon, but by an anti-horizon. It would still have mass, and so you would still be gravitationally attracted to it. But you could never enter it. The anti-horizon is the ultimate exclusive club. It forbids passage into the white hole, just as a black hole's event horizon forbids passage out of it. If you were to find yourself inside a white hole at the moment of its formation, however, you would not stay there for long. You would be propelled outwards, carried on a torrent of space-time that was itself expanding faster than the speed of light, an irresistible river from which you could not deviate until you were ejected from the white hole's anti-horizon. The white hole would continue this process, spewing out all the matter and radiation that had been trapped within it at its creation, until it was completely empty, leaving behind nothing but a bare singularity and its anti-horizon. A white hole is a cosmic ghost, an echo from the past, an explosion that is happening now, but which was set in motion at the beginning of time. In time, astronomers would find a much more natural and compelling explanation for the immense energy of quasars. They are the supermassive black holes at the centers of young, active galaxies. And the intense light they emit is the death scream of the matter that is spiraling into them. The idea of white holes as real, astrophysical objects faded from the mainstream. But as late as 2014, Novikov himself still held out hope that some of the strange, transient events we see in the sky could be the dying embers of primordial white holes, forged in the exotic, unknown physics of the early universe, and still shining today. And while most physicists today have relegated white holes to the dustbin of interesting, but physically impossible, mathematical curiosities, the idea did not die completely. A few brilliant and open-minded physicists were intrigued. One of them was the British mathematical physicist Roger Penrose, who would later go on to win a Nobel Prize for his groundbreaking work on the inevitability of singularities in black holes. Penrose became aware of Novikov's work and realized that it might just be the missing ingredient needed to make sense of another, even stranger, solution to Einstein's equations, a solution that seemed to describe a tunnel, a bridge, from one universe to another. But it would be Penrose's friend and frequent collaborator, the flamboyant and brilliantly imaginative American physicist John Archibald Wheeler, who would take this idea and run with it, who would give these strange cosmic tunnels their modern, evocative name, wormholes. Wheeler realized that the two strange beasts of relativity, the black hole and the white hole, could be stitched together, that they could be two mouths of a single, continuous tunnel through the fabric of space-time. And he realized that the mathematical description of this strange, connected object had, in fact, already been found, decades earlier, by a quiet and relatively unknown assistant of Einstein's. And with that solution in hand, Wheeler saw the dazzling possibility that this obscure mathematical branch of relativity could blossom into something truly extraordinary, a way to travel between the stars, to jump light years in an instant. He just needed to figure out if the machine of general relativity was spitting out a work of profound predictive genius, or a piece of beautiful, but ultimately misleading, mathematical madness. The history of science is filled with stories of unsung heroes, of brilliant minds who made crucial contributions but who, for reasons of personality, of politics, or of simple historical accident, have been largely forgotten, their names relegated to the footnotes of textbooks, forever living in the shadow of the giants of their time. The story of modern physics is, in many ways, the story of Albert Einstein. But Einstein did not work in a vacuum. He was surrounded by a constellation of brilliant collaborators, of friends, of rivals, of assistants, who helped him to develop, to refine, and sometimes to correct his revolutionary ideas. His close friend, Michel Besso, was, in Einstein's own words, the best sounding board in Europe. His first wife, Mileva Maric, was a brilliant physicist in her own right, and the extent of her contribution to his early, groundbreaking work is still a subject of historical debate. And then there was Nathan Rosen. Rosen would meet Einstein for the first time in 1934 at the newly founded Institute for Advanced Study in Princeton. He was a young, smart, and hard-working physicist who had already made a significant, if unheralded, contribution to our understanding of the atomic nucleus. But despite his own considerable intellect, it is unlikely that his name would be remembered today were it not for his 3-year collaboration with the great master of relativity. Rosen had been at Princeton for several months before he finally worked up the courage to knock on the door of the legendary physicist. Einstein was in the middle of a deep conversation with another collaborator, but he immediately put the young, timid Rosen at ease. Rosen later recalled, "I told him about my work, and he seemed interested and asked many questions. After a while, he began telling me about the work he was doing, and before I realized it, the three of us were engaged in a lively discussion. And what followed was a close and fruitful partnership. Officially, Rosen was Einstein's assistant, but their relationship was more like that of a mentor and a gifted student, and eventually, a friendship." Rosen was one of the few physicists who was genuinely interested in Einstein's then unfashionable and ultimately doomed quest to unify gravity with electromagnetism, a shared, quixotic passion that likely helped to cement their bond. And it was during this time together, while wrestling with the deep and thorny problems at the heart of Einstein's theories, that Rosen would come up with a remarkable, and at the time, completely overlooked, new possibility from the machine of relativity. Einstein in the 1930s was deeply troubled by two features of modern physics. The first was the appearance of singularities in his own theory of general relativity. These points of infinite density and curvature that seemed to signal a breakdown of the theory itself. The second was the growing consensus in the new field of quantum mechanics that elementary particles, like electrons, were true, point-like entities, with no size or spatial extent. Einstein found both of these ideas to be philosophically and aesthetically repugnant. He was a deep believer in the idea of a field theory of matter, the idea that particles were not fundamental, but were instead localized, stable, and smooth concentrations of a continuous field, like a knot in the fabric of space-time. He was searching for a way to modify his theory to eliminate the ugly singularities and to describe particles as these kinds of smooth, field-like structures. And it was the young Nathan Rosen who came up with a brilliantly ingenious and deeply strange way to do it. Rosen and Einstein imagined what would happen if you could follow a path into a black hole across its event horizon, but somehow avoid the crushing singularity at its center. They asked the machine of general relativity what is the simplest geometric construction that would allow for such a path, and the machine gave them an answer. It showed them that it was possible to mathematically stitch the space-time of a black hole to the space-time of its time-reversed twin, the white hole. The result was a smooth, continuous, and singularity-free geometry. A bridge that connected two different regions of space-time. A particle falling into the black hole would not hit a singularity, but would instead travel through this bridge and emerge from the white hole, either in a different part of our own universe, or, even more bizarrely, in an entirely separate, parallel universe. Rosen and Einstein then tried to take this idea a step further. They added electromagnetic fields to their calculations, hoping that these Einstein-Rosen bridges could serve as their long-sought-after model for elementary particles, with the electric charge of a particle being represented by the electromagnetic field lines that were threaded through the bridge. Unfortunately, this attempt to build a unified field theory of matter did not work. The model did not correctly reproduce the known properties of particles, and so the idea of the Einstein-Rosen bridge, a beautiful and ingenious piece of mathematical physics, fell into relative obscurity, a footnote in the history of a failed research program. It would be another 2 decades before the American physicist John Archibald Wheeler would resurrect this forgotten idea of Nathan Rosen's, dust it off, and give it a new and wonderfully evocative name, the wormhole. Wheeler, with his boundless curiosity and his penchant for asking the big, norming questions, immediately saw the profound implications of the Einstein-Rosen bridge. He was the one who realized that these were not just abstract, mathematical constructs. They were, in principle, tunnels through space-time, shortcuts that could connect distant points in the universe. In principle, you could travel to a star hundreds of light-years away, with no more effort than taking a leisurely stroll through a short cosmic tunnel. The dream of interstellar travel, of a future where humanity could become a truly galactic species, seemed to be hidden, in plain sight, in the forgotten equations of Einstein and his young assistant. But almost as soon as he had this exhilarating realization, Wheeler, a master of the complexities of general relativity, also saw the fatal flaws. Rosen and Einstein had imagined a purely geometric and static object. They had not asked the crucial, dynamic question that the 4-year-old Wheeler had once asked his mother: what happens when you get to the end of things? What happens when you actually try to travel through one of these wormholes? Wheeler, who was one of the few physicists in the West to have become aware of Novikov's work on white holes. Realized that the Einstein-Rosen bridge was a tunnel with a black hole at one end and a white hole at the other. And he knew that both of these objects were deeply, and perhaps insurmountably, problematic. The first fatal flaw is that while our universe seems to be full of physically plausible mechanisms for creating black holes, the collapse of massive stars being the most common, it seems to have no way of creating white holes. The laws of thermodynamics, particularly the second law of increasing entropy, seem to forbid it. The collapse of a star into a black hole is a process that dramatically increases the entropy of the system. It is a natural and thermodynamically favored process. But the time-reversed process, the spontaneous emergence of a star from a white hole, would be a massive violation of the second law, a process of incredible, unspontaneous ordering. It is like expecting a scrambled egg to spontaneously unscramble itself back into a pristine, whole egg. The universe simply does not work that way, even if a primordial white hole had somehow been formed in the exotic, unknown physics of the Big Bang. It would not be stable. Its anti-horizon is a place of infinite instability. Any tiny amount of matter or radiation falling towards it from the outside universe would be blue-shifted to an infinite energy, causing the white hole to collapse into a black hole in an instant. The universe, it seems, has a deep and powerful prejudice against white holes. They are a mathematical possibility that is forbidden by the rest of physics. But even if you could, by some magical future technology, create a stable white hole and use it as the exit of an Einstein-Rosen bridge, Wheeler realized that you should never, ever enter it. The interior of a wormhole is not a serene, peaceful tunnel. It is a region of the most extreme and violent gravitational forces imaginable, the same forces that crush matter at the singularity of a black hole, the tidal forces that would stretch an infalling astronaut into a long, thin strand of atoms in a process that physicists playfully call spaghettification, are at play within the throat of a wormhole. Wheeler's calculations showed that the wormhole is dynamically unstable. The very presence of a particle, or even a single photon of light, attempting to travel through it would be enough to trigger a catastrophic collapse. The wormhole would stretch along its length and compress across its middle, like a rubber band that is stretched too far and snaps. And this collapse would happen faster than the speed of light. Nothing, not even light itself, could travel through the throat of the wormhole and emerge safely from the other side before the tunnel destroyed itself. For a brief, fleeting instant, you might glimpse your destination. Light from the other end of the wormhole can fall into the throat. You could, in principle, see the distant stars of the Andromeda Galaxy. You could even meet another, equally unfortunate traveler who had entered from the opposite end. You could share a final, brief, and poignant moment. Two explorers from different ends of the universe, meeting in the heart of a dying, impossible bridge. And then, the wormhole would collapse, and you would be trapped, not in a white hole, but in the familiar, and equally deadly, heart of a black hole. Your only possible destination, the singularity. You would die. Wheeler's devastating analysis, published in the early 1960s, seemed to be the final nail in the coffin for the dream of interstellar travel through wormholes. For decades, most physicists accepted that they were, quite literally, dead ends, a beautiful but ultimately forbidden solution to Einstein's equations. But predictably, that was not quite the end of the story. For decades later, a new generation of physicists, armed with new ideas and a new sense of playful, speculative curiosity, would take up the challenge once again. And it would be one of Wheeler's own. Brilliant former students who would find a new, and even stranger, way to prop open the gates to the stars. He just needed a little help from the world of science fiction. The relationship between science and science fiction is a long, intimate, and often fruitful one. Science fiction writers have often been inspired by the cutting-edge ideas of science, taking them and extrapolating them into strange and wonderful new worlds. And in turn, scientists have sometimes been inspired by the bold, imaginative visions of science fiction, using them as a spur to ask new questions and to explore new theoretical possibilities. The story of the traversable wormhole is a beautiful example of this creative, two-way street. In the mid-1980s, the renowned astronomer and science communicator Carl Sagan was writing his first and only science fiction novel, Contact. The story involved humanity receiving a detailed set of instructions from an advanced extraterrestrial civilization for building a machine that would allow for interstellar travel. Sagan, a stickler for scientific accuracy, wanted his method of travel to be at least plausible, to be grounded in our best current understanding of physics. He initially considered having his protagonist travel through a black hole, but he knew that this would be a one-way trip to a crushing singularity. So, he turned to his old friend and colleague, the theoretical physicist Kip Thorne, one of the world's leading experts on general relativity and black holes. Sagan asked Thorne a simple question: what is the most plausible, scientific way to get my character from here to the star Vega, 26 light-years away, in a reasonably short amount of time? Thorne, aware of the fatal instabilities of the classic Einstein-Rosen bridge, was initially stumped, but the question intrigued him. It was a well-posed physical problem, and he decided to take it seriously, working with his graduate students, Michael Morris and Ulvi Yurtsever. Thorne went back to the machine of general relativity, but instead of working it in the forward direction, starting with matter and calculating the resulting space-time, he decided to work it in reverse. He started with the desired output, a stable, traversable wormhole, a space-time geometry that would connect two distant points and that would not contain any deadly singularities or event horizons. He then asked the equations the crucial question: what kind of matter or energy would you need to input to create and sustain such a structure? The machine, ever dutiful and completely ignorant of what is and is not physically possible in the real universe, gave him an answer. And the answer was as strange as it was profound: to build and maintain a traversable wormhole, you would need a form of matter or energy with a very peculiar and seemingly impossible property: a large negative pressure, a pressure that is, in fact, greater in magnitude than its energy density. This is what physicists now call exotic matter. This is not to be confused with antimatter, which has a positive mass energy and a positive pressure, just like normal matter. This is something else entirely, something that would have to have a negative mass energy. A football that weighs minus 500 grams, a steak that has a negative caloric content, exotic matter, if it existed, would have bizarre anti-gravitational properties. It would not pull and attract, it would push and repel. It would be the ultimate source of cosmic anti-gravity. And Thorne and his students realized that this was exactly what was needed to solve the two fatal problems of the classic wormhole. A shell of this exotic, repulsive matter, placed at the throat of a wormhole, would act like a cosmic scaffolding. Its anti-gravitational push would counteract the wormhole's natural tendency to collapse. It would hold the throat open, making it stable, and it could be used to push the entrance of the wormhole outside of any event horizon, making it safely traversable. You could enter one end, travel through the stable, open throat, and emerge from the other, without being crushed by tidal forces or trapped by a singularity. The key to the stars, it seemed, was this strange, hypothetical, and deeply problematic substance exotic matter. Thorne's work, which he published in a 1988 paper, was never intended as a serious proposal for building a wormhole. As the paper's playful subtitle, "A Tool for Teaching General Relativity," suggested, it was primarily a pedagogical exercise, a way to use a fun science-fictional problem to explore the deep and often counterintuitive consequences of Einstein's theory. As Thorne himself said, "Almost everything that I've done was something I never planned to do, but the idea took on a life of its own." It sparked a new wave of research into the theoretical possibilities of wormholes, and it forced physicists to confront a deep and important question: is exotic matter, in any form, actually allowed by the laws of nature? The problem with exotic matter is not just that we have never observed it, it is that its existence would seem to violate some of the most fundamental and cherished principles of physics. A substance with negative mass energy would have deeply paradoxical properties. For example, it would seem to violate the conservation of momentum. If you pushed on an object with negative mass, it would accelerate towards you, not away from you. This would allow you to create a reactionless drive, a device that could accelerate itself without expelling any propellant, a clear violation of Newton's third law. It could also lead to runaway solutions, where a positive mass and a negative mass object would chase each other, accelerating to infinite speed without any input of energy, a clear violation of the conservation of energy. For these reasons, most physicists believe that macroscopic, stable quantities of exotic matter are likely forbidden by the laws of nature. But what about exotic energy? We know from Einstein's famous equation, E = mc squared, that matter and energy are two sides of the same coin. And the quantum world, we have learned, is a strange and wonderful place, a place where our classical intuitions often fail. And it is in the quantum world that we find a small but tantalizing loophole, the Casimir effect. As we have seen, the energy of the quantum vacuum is not zero, but it is possible to create a region of space where the energy density is less than the normal energy density of the surrounding vacuum. The space between the two parallel metal plates in the Casimir experiment is just such a region. Relative to the outside vacuum, this region has a negative energy density. This is a real, measurable, and experimentally confirmed example of a violation of one of the classical energy conditions, a set of rules of thumb that physicists have developed to distinguish between physically plausible and unphysical solutions to Einstein's equations. The Casimir effect violates the weak energy condition, which states that the local energy density, as measured by any observer, must always be non-negative. However, the Casimir effect is a very small and very localized phenomenon, and it is not yet clear if it is possible to collect and concentrate this negative energy in a way that would be sufficient to stabilize a macroscopic wormhole. There are theoretical arguments, known as quantum inequality theorems, which seem to suggest that while you can have localized pockets of negative energy, they must always be balanced by larger regions of positive energy, and that there are fundamental limits on how much negative energy you can have for how long. The question of whether it is possible to create a sufficient amount of stable, macroscopic negative energy to build a wormhole remains one of the most important and most difficult open questions in fundamental physics. Its answer is likely tied to the still unknown theory of quantum gravity. But the possibility, however remote, remains, and it has given us a new and deeply profound way to think about the nature of space. The same quantum vacuum that is the source of the universe's expansion, the same void that is the cradle of all matter, may also contain the secret to transcending the vast cosmic distances that separate us from the stars. A traversable wormhole, if it is possible at all, would be a thing of true wonder. Its entrance would be a shimmering, spherical portal, not unlike the event horizon of a black hole, but it would not be black. It would be a blaze of light, a window into another part of the universe. Looking into it, you would see the distorted, gravitationally lensed image of the stars and galaxies at its other end. You could wave hello to a friend in another galaxy. And you could, in principle, step through and travel there yourself. The journey through the wormhole's throat, held open by the delicate anti-gravitational pressure of negative energy, would be a strange one. Your view of the outside universe would be warped and distorted in bizarre ways by the extreme geometry of the tunnel. But if it were properly engineered, the tidal forces would be gentle, and you would pass through unscathed, arriving at your destination in a time that could be, from the perspective of an outside observer, shorter than the time it would take light to travel the same distance through normal space. It is a tantalizing and beautiful vision. But a functioning wormhole, as we are about to see, is more than just a bridge to faraway galaxies. It is also, and almost unavoidably, a tunnel into the past. On the 28th of June, in the year 2009, at precisely 12 noon Universal Time, the great astrophysicist Stephen Hawking sat alone in a festively decorated room at the University of Cambridge, surrounded by balloons and a tray of champagne. He was waiting for his guests to arrive, but no one came. After several hours, he departed, and only then, after the party was over, did he send out the invitations. The invitation, beautifully printed and elegantly worded, read, "You are cordially invited to a reception for time travelers." It gave the precise date, time, and coordinates of the party. Hawking's charming and clever experiment was designed to provide a simple, empirical test of the possibility of time travel. "I'm hoping copies of the invitation, in one form or another, will survive for many thousands of years," he later said. "Maybe one day, someone living in the future will find the information and use a wormhole time machine to come back to my party, proving that time travel will one day be possible." The fact that no one showed up was, for Hawking, a compelling piece of evidence that travel into the past is likely not possible. And yet, the very theory that he had dedicated his life to studying, Einstein's general theory of relativity, seems to allow for it, and wormholes are the key. If you could build a stable, traversable wormhole, you could, almost by accident, turn it into a time machine. The recipe is surprisingly simple. You create a wormhole with its two mouths, A and B, initially at rest next to each other. Then, you take one of the mouths, say mouth B, and put it on a spaceship and take it on a round trip at a very high speed, close to the speed of light. According to Einstein's special theory of relativity, time for a moving observer slows down relative to a stationary observer. This is the phenomenon of time dilation. So, when mouth B returns from its journey, its internal clock will be lagging behind the clock of the stationary mouth, A. Let's say, for example, that from the perspective of mouth A, 10 years have passed, but for the traveling mouth B, only 1 year has passed. Now you have a tunnel that connects two different points in time. If you enter mouth A in the year 2010, you will travel through the wormhole and emerge from mouth B in the year 2001. You have traveled 9 years into the past. The wormhole is not just a shortcut through space. It has become a shortcut through time. This possibility, which is a direct and unavoidable consequence of combining the geometry of a wormhole with the principles of special relativity, opens up a Pandora's box of logical paradoxes that have troubled physicists and philosophers for decades. The most famous of these is the grandfather paradox. What if you travel back in time and prevent your own grandfather from meeting your grandmother? Then your parent would never have been born, and therefore, you would never have been born. But if you were never born, how could you have traveled back in time to prevent their meeting in the first place? The logic seems to fold back on itself in an inescapable contradiction. This is just one of a host of similar consistency paradoxes. What if you go back in time and destroy the very wormhole machine that you use to travel back in time? The very act of succeeding in your mission erases the possibility of you ever having undertaken it. Faced with these seemingly insurmountable logical hurdles, physicists who have studied wormholes and time travel have been forced to come up with some ingenious and often bizarre ways to resolve them. The Soviet physicist Igor Novikov, the father of the white hole, proposed what is now known as the Novikov self-consistency principle. He suggested that the laws of physics are such that they forbid any action that would create a paradox. Time travel into the past may be possible, but you are not free to do whatever you want. Your actions are constrained in such a way that they must be part of a self-consistent historical loop. If you travel back in time to try and kill your grandfather, you will fail. The gun will jam, you will slip on a banana peel, you will have a sudden change of heart. The universe, in a sense, will conspire to protect its own. Causal consistency. The past is not changeable, it is fixed. And if you have traveled into it, then your actions were already a part of that fixed history. This is a logically consistent solution, but it is one that seems to do away with the very notion of free will. Stephen Hawking, on the other hand, took a different approach. He proposed what he called the chronology protection conjecture. He believed that the laws of physics themselves must have a built-in mechanism that forbids the formation of closed time-like curves. The technical term for paths through space-time that would allow for travel into the past. He did not know what this mechanism was, but he believed that a full theory of quantum gravity would reveal it. Perhaps the very act of trying to turn a wormhole into a time machine would cause a catastrophic buildup of quantum vacuum energy that would destroy the wormhole in an instant. The universe, in his view, has a chronology protection agency that makes the world safe for historians. A third, and even more radical, possibility comes from the many worlds interpretation of quantum mechanics. In this view, when you travel back in time and alter the past, you do not change the history of your own universe. Instead, your action causes the universe to split into a new, parallel timeline. You have not changed your past, you have created a new one. In this new universe, your grandfather is dead and you will never be born. But in your original universe, nothing has changed. You have simply traveled to a different branch of the multiverse. This elegantly solves the paradoxes, but it does so at the cost of accepting the existence of an infinite number of parallel realities. In this scenario, perhaps there is a universe out there where Hawking's party was a roaring success, attended by a throng of curious and well-behaved time travelers. But in our branch of the multiverse, it was a lonely and ultimately unsuccessful affair. The question of whether wormholes and by extension time travel are possible remains one of the most fascinating and unresolved questions in all of fundamental physics. It is a question that lies at the deep and treacherous intersection of general relativity, quantum mechanics, and the very nature of causality and time. And it is a question that has, in recent years, taken another unexpected twist. In 2019, a team of researchers at Harvard and the Institute for Advanced Study, the very same institution where Rosen and Einstein had first conceived of their space-time bridge, found a way to construct a theoretical, traversable wormhole that did not require any exotic, negative energy at all. But there was a catch. This wormhole, which was constructed in a simplified, toy model of space-time, was not a shortcut. In fact, an analysis of its geometry revealed that the path through the wormhole was actually longer than the path through the surrounding normal space. It was not a cosmic highway. It was a cosmic scenic route. This intriguing, if frustrating, Result suggests a new and tantalizing possibility that wormholes may very well be allowed by the laws of nature, but they may also be completely and utterly useless for interstellar travel. The current consensus among most physicists is that traversable wormholes, at least the kind that would allow for faster-than-light travel or time travel, are likely forbidden by a deeper and as yet unknown principle of quantum gravity. But they remain an invaluable theoretical laboratory, a playground for the mind where we can test the limits of our current theories, explore the most extreme configurations of space-time imaginable, and probe the deep and beautiful mysteries that lie at the heart of our understanding of the universe. As Stephen Hawking himself once said, reflecting on the deep and beautiful mysteries of quantum gravity, not only does God play dice, but he sometimes throws them where they cannot be seen. Wormholes may be one of those dice, a hint of a deeper, stranger, and more wonderful reality. A reality that is, for now, hidden from our view.